All right, let's dive right in. Today, we are opening one of the biggest cases in all of science, maybe the biggest. We're calling it the case of the missing universe. Think of it like a cosmic detective story. We're going to follow the clues to try and get our heads around two of the most mind-bending mysteries out there, dark matter and dark energy. So let's get to it. The story starts with a single, absolutely shocking fact.
So get this. Everything we can see, every star, every planet, every galaxy, you, me, this microphone, all of it, makes up less than 5% of the universe. The rest of it, a staggering 95%, is completely invisible. We can't see it, we can't touch it, it's just missing.
So the most obvious question in the world is, what is all that other stuff? Well, our investigation shows it's not just one thing. It's two completely different, mysterious entities, and they're locked in a battle for the fate of the entire universe.
Yeah, that 95% enigma is split between our two main suspects, dark matter and dark energy. And what's so fascinating is that they are complete opposites. They're in a constant cosmic tug-of-war, literally pulling the universe in opposite directions.
Okay, so here's the core difference. On one side, you have dark matter. Think of it like a cosmic glue. It's got gravity, so it's an attractive force. It pulls things together, it forms these huge, clumpy structures that galaxies live in. Then on the other side, you have dark energy. This stuff is weird. It's like a cosmic accelerator. It's a repulsive force that's spread out smoothly everywhere, and it's literally pushing the fabric of space apart. So one pulls things together, the other pushes everything away.
Let's start with our first trail of evidence. These are the clues that first made astronomers realize there had to be some kind of invisible cosmic glue holding everything together. This is the case for dark matter.
So back in the 1970s, the astronomer Vera Rubin was watching galaxies spin. Now, common sense and the laws of gravity tell you that stars on the outer edge of a galaxy should be moving way slower than stars in the middle, right? Just like how Pluto moves way slower than Mercury in our solar system. But that is not what she found. Not even close. The stars on the edge were moving just as fast as the ones near the center. The only way that's possible is if the entire galaxy is sitting inside a giant invisible halo of matter, something that provides a ton of extra gravity. Without it, these galaxies would have spun themselves apart billions of years ago.
And we are not talking about a small discrepancy here. To make the math work, to explain those crazy rotation speeds, galaxies need to have 5 to 10 times more dark matter than all the visible stuff, all the stars and gas put together. It's not just an ingredient, it's the main ingredient.
And if you need more proof, here's the smoking gun. It's an event called the bullet cluster. This is what happened when two galaxy clusters crashed into each other. Scientists watched it happen, and they saw the normal matter, the hot gas, smash together and slow down, just like you'd expect. But the gravity, the bulk of the mass, just passed right through itself like a ghost. It was a clear, visual separation of the normal stuff from some invisible mass that only feels gravity. In other words, definitive proof of dark matter.
But here's the plot twist. Just when scientists were getting comfortable with the idea of dark matter, a discovery in 1998 just blew the whole investigation wide open. It pointed to a second suspect, one that's arguably even weirder.
You know, for most of the 20th century, everyone just assumed one thing. The expansion of the universe that started with the Big Bang had to be slowing down. Of course it was. Gravity pulls things together. The only real debate was whether it would slow down forever or if gravity would eventually win and pull everything back together in a big crunch. Seemed pretty straightforward, right?
Wrong. Totally, completely, shockingly wrong. In what has to be one of the biggest upsets in the history of science, astronomers discovered the exact opposite was happening. The expansion of the universe is speeding up. So how on earth did they figure that out? They used these special explosions called Type I supernovae. The key thing about them is that they are standard candles. They all go off with the same predictable brightness. So they're like cosmic 100-watt light bulbs. If you see one that looks dim, you know it's really, really far away. Well, when astronomers looked at the most distant ones, they were way dimmer and therefore way farther away than any of our models predicted. Something had to be pushing them away faster than expected. This totally rewrote the history of the universe. It's like a two-act play. In Act 1, for the first 9 billion years or so, regular matter and dark matter were in charge. Gravity was winning and the expansion was in fact slowing down. But then, about 5 billion years ago, Act 2 began. This mysterious repulsive force, this dark energy, became dominant, and the universe entered this era of runaway acceleration that we find ourselves in today.
So, to explain all this, cosmologists have put together an official story. It's called the Standard Model of Cosmology, and it does a pretty good job. But lately, some serious plot holes have started to show up. The story is starting to crack.
This official story is called the Lambda-CDM model. It's basically our current cosmic inventory. It states with incredible precision that the universe is about 68% dark energy, almost 27% cold dark matter, and just under 5% normal matter. And look, this model is fantastically successful. It explains almost everything we see on the largest scales. Almost.
Which brings us to the biggest crack in the whole theory. It's a problem called the Hubble tension. Here's the deal. When scientists use our best model of the early universe to predict how fast the universe should be expanding today, they get a number around 67. But when other astronomers go out and directly measure the expansion using things like those supernovae, they get a different, faster number, around 73. These two numbers, which come from completely independent methods, absolutely should match. But they don't. And that gap is the biggest headache in all of cosmology right now. This tension, plus the fact that we still have no clue what our two main suspects actually are, has launched what is easily one of the greatest scientific hunts of all time.
When it comes to dark matter, there are two main suspects in the lineup. For a long time, the favorite was the WIMP, a weakly interacting massive particle, a real heavyweight. But after years of searching with no luck, a new lightweight contender is getting a lot of attention, the axion. It's an incredibly light particle that has the added bonus of solving another totally separate problem in physics, killing two birds with one stone, maybe.
So the search for these particles is happening on three fronts. You've got scientists in labs deep underground trying to directly catch a WIMP as it smacks into their detector. You have astronomers pointing telescopes at space, hoping to indirectly see the flash from two WIMPs annihilating each other, and you have physicists at the Large Hadron Collider trying to smash particles together hard enough to actually create a WIMP from scratch. So far, nothing definitive. The culprits are still at large.
But don't lose hope, because the investigation is getting a massive upgrade. A whole new generation of cosmic detectives is firing up. We're talking about the Vera Rubin Observatory and the Euclid Telescope, which will map the dark universe with ridiculous precision. And on the ground, detectors like Lux Zeppelin and ADMX are building the most sensitive WIMP and axion traps ever. The hope is that one of these will finally give us the breakthrough clue we need.
And that leaves us with the final, absolutely critical question. What's the final verdict going to be? Are we on the verge of finally nabbing these cosmic culprits, figuring out what they are, and closing the case of the missing universe? Or are these cracks we're seeing, like the Hubble tension, telling us the mystery is even deeper? That the solution isn't just finding a new particle, but that we have to fundamentally rewrite the rules of gravity and physics as we know them. The hunt is on. And the next discovery could literally change everything we think we know.